The User Datagram Protocol, UDP, stands as a fundamental communication protocol within the Internet Protocol Suite, facilitating the transmission of messages in the form of datagrams across hosts on an IP network. Unlike protocols that require prior setup of communication channels, UDP functions without the need for pre-established connections or data paths. As a connectionless protocol, UDP omits the negotiation of connections and does not retain a record of sent messages. It ensures data integrity through checksums and utilizes port numbers for directing different functions at the datagram's source and destination. Operating without handshaking dialogues, UDP exposes the user's program to the network's unreliability, offering no assurances of delivery, ordering, or duplicate protection. In cases where error correction is crucial at the interface level, applications may opt for Transmission Control Protocol, TCP, or Stream Control Transmission Protocol, SCTP, specifically designed for this purpose. UDP proves ideal for applications where error checking and correction are either unnecessary or handled within the application, thereby circumventing the overhead associated with processing in the protocol stack. Applications with time-sensitive requirements often leverage UDP due to its preference for dropping packets over waiting for delayed transmissions caused by retransmission delays, a critical consideration for real-time systems. Initially conceptualized by David P. Reed in 1980, UDP was formally defined in RFC 768. While UDP ensures the integrity of data through checksums, it does not guarantee message delivery or maintain message state once sent, hence its nickname, Unreliable Datagram Protocol. Applications requiring transmission reliability must handle this at the user level. UDP's characteristics make it ideal for specific scenarios. It is transaction-oriented, making it suitable for query response protocols like Domain Name System and Network Time Protocol. Furthermore, its datagram approach is fitting for modeling other protocols like IP tunneling or remote procedure call, as well as network file system. Due to its simplicity, it is apt for tasks like bootstrapping and foregoing a full protocol stack, commonly seen in protocols such as DHCP and Trivial File Transfer Protocol. Stateless nature enables large client numbers, as seen in applications like IPTV, and its lack of retransmission delays makes it ideal for real-time applications such as voice-over IP and online games that rely on real-time streaming protocol. Support for multicast makes it valuable for distributing information widely, such as in service discovery or shared data scenarios like Precision Time Protocol and Routing Information Protocol. Applications utilize datagram sockets for establishing host-to-host communications by binding a socket to the endpoint of data transmission defined by an IP address and a port. Through this process, UDP enables application multiplexing. A port, distinguished by a 16-bit integer value known as the port number, can take on values ranging between 0 and 65535. Although port 0 is reserved, it can serve as a valid source port value if the sending process does not anticipate responses. The Internet Assigned Numbers Authority, IANA, has segmented port numbers into 3 categories. The first category includes port numbers 0 to 1023 allocated for well-known services. To utilize these ports on Unix-like operating systems, superuser permissions are required. Following this, port numbers 1024 to 49151 fall under registered ports, designated for IANA-registered services. Lastly, ports 49152 to 65535 are dynamic ports that lack official assignment to any specific service and are open for general use. These ports are also utilized as ephemeral ports, allowing software on the host to dynamically create communication endpoints as necessary. A UDP datagram comprises a datagram header followed by a data section serving as the payload data for the application. The UDP datagram header includes 4 fields, each spanning 2 bytes, 16 bits per field. The header fields are the source port, destination port, length, and checksum. The source port field utilizing 16 bits indicates the originating port, crucial for potential replies. It is common for client hosts to use ephemeral port numbers, while server hosts typically utilize well-known port numbers ranging between 0 to 1023. The destination port field, also 16 bits, specifies the receiving port and is essential for communication. Ephemeral port numbers are typically used by client destination hosts, while well-known port numbers are prevalent for server destination hosts. The length field, consisting of 16 bits, denotes the size in bytes of the UDP datagram, encompassing both the header fields and the data field in octets. The minimum length allowed is 8 bytes, which accounts for the header. Theoretically, the field size permits a maximum of 65,535 bytes, 8-byte header plus 65,527 bytes of data for a UDP datagram. Nonetheless, due to limitations imposed by the underlying IPv4 protocol, the actual data length is restricted to 65,507 bytes, 65,535 bytes, 8-byte UDP header, 20-byte IP header. Meanwhile, the checksum field, spanning 16 bits, serves for error checking purposes on the header and data. It is optional in IPv4 but is typically mandatory in IPv6 implementations. Finally, the data field in the UDP datagram encompasses the payload of the UDP packet, with a variable length depending on the specific application. The checksum calculation in UDP is essential for error detection during data transmission. In IPv4, a pseudo-header is created to compute the checksum, which includes the source and destination addresses, protocol type, UDP length, and data. The checksum result is the one's complement of the sum of these elements. If the checksum value is 0, it is sent as one's complement to indicate no computation occurred, as all zeros and ones are equivalent in one's complement arithmetic. Optional checksum usage is permitted in IPv4, where a 0 value is used if no checksum is applied. In IPv6, due to the larger address space and header structure, the checksum computation method is adjusted. The pseudo-header for IPv6 includes the 128-bit addresses, UDP length, zeros field, and next header protocol type. The checksum calculation in IPv6 involves summing the fields mentioned and taking the one's complement to generate the UDP checksum value. Unlike IPv4, the checksum is mandatory in IPv6, and specific conditions allow for a UDP 0 checksum mode with a tunnel protocol. This change in IPv6 aims to ensure accurate data transmission and integrity checks in network communication protocols. UDP applications may experience packet loss, errors, or duplication due to their lack of reliability. In instances where UDP is used, end-user applications are required to implement necessary handshaking mechanisms to confirm real-time message reception. Some applications, like TFTP, can integrate basic reliability features at the application layer as needed. For scenarios demanding a high level of reliability, the Transmission Control Protocol, TCP, is often preferred. Typically, UDP applications do not utilize reliability mechanisms, as they might impede the application's functionality. Common examples of UDP applications include streaming media, real-time multiplayer games, and voice-over IP, VoIP. In these cases, packet loss is usually manageable, with concerns revolving more around latency and jitter, particularly in VoIP applications. Notably, TCP could introduce jitter if packets were lost, as it does not provide data to the application during a resend request for missing information. Various critical Internet applications rely on UDP, such as the Domain Name System, DNS, Simple Network Management Protocol, SNMP, Routing Information Protocol, RIP, and Dynamic Host Configuration Protocol, DHCP. Voice and video traffic commonly utilize UDP for transmission. Real-time video and audio streaming protocols are designed to handle occasional packet loss without significant quality degradation, avoiding extensive delays from retransmissions. In response to an uptick in UDP traffic from real-time applications in the mid-2000s, some businesses noticed performance issues in TCP-dependent systems like point-of-sale, accounting, and databases. TCP's tendency to reduce data rate usage upon detecting packet loss could lead to hindrances. Certain VPN systems, such as OpenVPN, leverage UDP for error checking at the application level while establishing reliable connections. WireGuard, also using UDP, conducts error checks without guaranteeing reliability, delegating this task to encapsulated protocols. Notably, QUIC operates as a transport protocol atop UDP, delivering a reliable and secure connection. HTTP 3 adopts QUIC over previous versions that utilize a mix of TCP and TLS for reliability and security, respectively. This consolidation reduces connection setup time by requiring only a single handshake, instead of separate handshakes for TCP and TLS.